Welcome learners to the course of Material Science offered by the School of Engineering Technology, Indira Gandhi National Open University. In our previous session, we have covered the tension test and the various properties of materials, stress and strain diagram, and other things also, like what is the effect on the brittle materials and the ductile materials as well. Today we will be discussing about the compression test. I am Shashank Srivastava from IIT IGNOU. So the compression test. So like we have seen in the earlier sessions that there are certain materials which are good in tension. So similarly, there are certain other materials which we can use for the compression loads. They are much better in the compression loads. Like for example, concrete, bricks, wood. These are very good in compression when the load is of compressive type. And to evaluate these materials, compression test is essential. So that's why we are discussing this compression test. So material behavior in general in the compression test is quite similar to that in the tension test. And we will be focusing in this lecture on the difference in the stress strain diagram when compression test is compared to the tension test, and also the mode of failure, especially in the case of ductile materials. So we start with the ductile materials. So in this case, as compared to the tension test case, we see that there is no ultimate compressive strength. In that case, there was an ultimate strength, but when we are doing the compression test, there is no ultimate compressive strength. And what is the reason behind that? The reason is that ductile material keeps on expanding in lateral directions as compressive load increases. Now you can see in the figure how it is happening. See, the compressive load is coming on this. There are two plates, one at the top and the other at the bottom. And the compressive load is acting, which is pushing it inwards. So what happens that at the ends where the plate is meeting the specimen tries to bulge. That is what is happening in the case of ductile material. So this lateral expansion is taking place and it continues to take place, whereby what happens? Area will increase, you are seeing here in the figure, and ultimately the specimen might be turned into a disc. Now you can see here in this figure there is the dotted curve, and this dotted curve represents the disc. If we keep on applying this compressive load, the ductile material will keep on taking the load and it will finally get converted into a disc, but it will not break. So the lateral bulging of a ductile material enables it to resist almost indefinitely large focus without fracture. That's why I told you earlier also that lateral bulging will keep on happening in case of ductile material, and it will be able to resist it without any fracture. So ability to undergo large plastic deformation under compression is called malleability of ductile materials, but this property cannot be defined quantitatively. So we cannot define malleability quantitatively, but as such one qualitative definition is there, which says that malleability is something when the material can be turned into sheets. Like may have seen somewhere in a steel plant or somewhere that there are sheets of certain kinds of steel. So that sheets can be made only when the material is malleable. So the modulus of elasticity and the modulus of resilience for ductile material can be evaluated in compression as in tension, but modulus of toughness cannot be defined. So it's a very important point here that modulus of elasticity and modulus of resilience both are defined in ductile materials and as well as in the compression test, but modulus of toughness cannot be defined. Why? Because here, as I told earlier, there is no ultimate compressive strength, meaning the material is not going to break. So we don't have any such ultimate compressive strength. That's why we don't have the modulus of toughness. So at atomic level, what happens? Unlike in the tensile stress case, no definite maximum exists in stress versus atomic bond curve. So no definite maximum is existing, and consequence is what? Because of this no definite maximum stress, what happens that there is no limit to repulsive force that can be built up between the atoms. So any amount of repulsive force can come in, but it cannot fracture the material. So there is no limit for that. And further conclusion, due to this, what will be the conclusion? Conclusion is that compression will not become the cause of failure and will always result in elastic strain. It is the shearing stress component which causes the slip of atomic planes and results in bulging of the specimen and plastic deformation. So we see here, it's very important that the compression will never result in the failure of the material, but the shearing stress component will lead to failure because they will slip along the planes. So here we see one diagram which will give us the comparison between the compressive stress and the tensile stress, what is happening in both the tests. So for compression, the elastic behavior in compression you see ends at higher values of stress. Now you see here in the figure, if you go into the third quadrant and the negative one, you see that the compressive stress is more magnitude wise, and you go in the first quadrant, you can see that the tensile stress magnitude wise is lesser. So that is the case. Elastic stress strain relationship in tension and compression is shown here, and we have seen that in compression it is more as compared to tension. So here is the behavior of the material rubber. So for rubber, you can see for materials like rubber, in tension the coiled molecules are first uncoiled, they are uncoiled and then strained, whereby such materials show low stiffness followed by higher stiffness in tension. So you can see here this curve, you can see this one, the compression one. At the lower level there is slight decrease in the stiffness, and then it goes on increasing, and it is going on increasing further and further. So demonstration will be here. Okay, I am giving you a demo about this rubber band, how it is acting upon application of the compressive stress or compressive load. See, I am pushing it like this. What is happening? It is coiling up, like it was said earlier in the lecture. In compression, further coiling in initial stage will happen, and then after this coiling, what will happen? Elastic compression of the molecules will take place. Then slight stiffening effect will happen, which will be in the vicinity of the decrease of stiffness, and further the stiffness will increase. So after talking about the compression of the ductile materials, let's talk about the compression of the brittle materials. For most brittle materials, the elastic properties like the elastic limit, modulus of resilience, yield strength and modulus of elasticity are same in tension and compression. So for brittle materials, whether we do the tensile test or the compression test, it is said that all these properties like the elastic limit, modulus of resilience, yield strength, all are same. Now what is different then? There is one point to remember. The ultimate compressive strength of most brittle materials is different than the ultimate tensile strength. So for brittle materials, if you do the tension test and if you do the compression test, so you will find that the ultimate compressive strength in case of brittle materials will be more than the ultimate tensile strength. As for example, concrete ultimate compressive strength is about 10 times its ultimate tensile strength. So here a compression test specimen is shown, and how it fractures. It fractures due to shearing along a plane inclined to the axis as shown in the figure, and the orientation of the plane of shear is affected by the presence of normal compressive stresses. So you can see this compressive stress is acting normally to the cross section. This will affect the plane of shear. So the consequence, what will be the consequence of that? We will see that the final fracture will not occur along the plane of maximum shearing stress, which is inclined at an angle of 45 degrees with the axis. So it will not occur along the axis which is inclined at an angle of 45 degrees with the axis. Instead, it will occur at a plane which may be at an angle between 35 and 45 degrees with the axis, and this is happening only because of the normal compressive stress. Now further we will see that there is some lateral bulging which tends to occur in brittle materials also. Like in the case of ductile materials, which we discussed earlier, lateral bulging may occur in brittle material also, but it is very less as compared to the ductile one. What happens is that friction between the platens, what is the platen? Platen is this top plate you can see, which is connected to the top and bottom of the specimen. The top one is the top platen, the bottom one bottom platen. So friction between the platens and the specimen ends greatly restrict the lateral deformation. So here at the ends where they are joining, this friction will restrict the lateral deformation. If it tries to deform, then it will restrict that. So this friction reduces for longer specimen. If my specimen is very long, then this friction will reduce. And one more thing can happen, that if it is too long, then there will be a tendency to buckle. Buckle meaning it can bend. A vertical column is there, suppose, and if the load is coming from the top through its axis, then it buckles or it bends. So that is what buckling is. To minimize the influences of friction and buckling, the length to diameter ratio of compression specimen has to be chosen very carefully. That's what earlier also we discussed, that due to the friction, this buckling effect and all those things are there, and lateral bulging may also happen. So in order to avoid all this, we will have to have appropriate length to diameter ratio. For determination of compression strength, actually this ratio is kept between 2 and 3. So if we want to determine the compression strength, it has to be between 2 and 3. But for determination of the elastic properties, the ratio of length to diameter may be chosen between 8 and 10. So whenever we want to determine certain elastic properties, then the length length to diameter ratio has to be between 8 and 10. And if it is less than 1.5, then what will happen? The fracture plane, it is generally about 45 degree to the axis, so it may intersect the end, which is undesirable. Like in the figure you can see this particular curve is going, and it may intersect your ends. So it is not at all desirable. So the brittle material in which the atomic bonds are not re-established will ultimately fracture due to slip, which may occur along one or several planes. This failure is called fragmentation. So this is called fragmentation. Now if it is slipping, it is occurring due to shear. This failure is occurring due to the shear. So one more thing we will see in case of the brittle materials compression test is that the cracks, pores and holes, actually they close up and they don't have too much effect on the brittle material. Instead they close up, and net compressive strength is higher than the tensile strength in this case. While the cracks, pores and holes play a very important role in reducing the tensile strength. So there is a difference. If the tensile strength is there, you can see the cracks, pores and holes reduce it, whereas in case of the compressive strength, they try to help that and they increase the compressive strength. So now we will discuss about the experimental procedure. How do we do the compression test, whether it be ductile material or whether it be brittle material. So very important in this is that the application of load and axial alignment. So the application of load and axial alignment are the two most important factors. So the platen, earlier discussed, the platen, normally the one in contact with the moving crosshead, is made self-aligning with a spherical head on the top of the plate, which is directly in contact with the specimen. So you can see here, you can see this bottom one, the bottom platen, it is in contact with the specimen, and at the other side it is connected to the crosshead. So this crosshead will be moving, and at the top of this specimen, the spherical surface is there. So the top platen will come in contact with this one, with this spherical surface. Actually spherical surface is given so that it fits in better, and it is better in alignment also. The center of the spherical head coincides with the center of the specimen top surface, as I told you, through which must pass the axis of the machine. So the axis, both the axes should be coincidental. There should not be any eccentricity, and thus we need to take great care to do this type of activity. So as we talked earlier, we have talked about the friction between the loading plate and the top of the specimen. And this friction between the loading plate and top of the specimen achieves a near hydrostatic stress. Hydrostatic stress, also known as volumetric stress, is a component of stress which has only uniaxial stresses and there is no shear component. So there is no chance of failure between the platens and the ends of the specimen as there is no shear. Meaning that this specimen will be acted upon by the compressive force from all the directions. So it will be equal from all directions and thus avoids failure of material. Because of this hydrostatic stress, failure will not be there just below the top where the platen is touching the specimen. As we move away from the top surface of the specimen, the compressive stress in direction perpendicular to the load axis. So you can see direction perpendicular to the load axis, meaning lateral direction. This is along the axis, and when we are putting the load from this lateral direction, it will be compressive stress. So this compressive stress decreases as we go along the length. Like this is the length of the specimen, and if we are moving away from the top towards the bottom, so we are going along the length of that specimen. So this compressive stress goes on decreasing, but it does not vanish completely. So that's why the length to diameter ratio is very important. So what is the recommendation then for that? Distance should be at least diameter of the specimen. So this length should be at least of diameter of this diameter, and length should be equal. Minimum, this is the minimum. For this reason, the specimen length of 3D is normally recommended. So generally what we do, we take the length to be 3 times of the diameter. In some specimens, close cut circular concentric grooves are created to hold lubricant, particularly in specimens of ductile material. So here concentric grooves will also be cut, and there the lubricant will flow in case of ductile materials. So this was one experimental procedure. There is another experimental procedure, that is the method 2. So in this method, what we are doing is that the ends are changed now. The ends are made in a conical hollow type of shape. You can see in the figure here. You can see this is somewhat like a cone. And why it is done like that? To receive similar loading plate. So the plate is also made accordingly. This is specimen and plate, you can see they are matching together, and both have certain kind of shape so that they can fit together. And the angle of the cone is equal to the angle of friction. You can see here, this is one alpha and phi. So one is the angle of the friction and one is the angle of cone. So both have to be equal in order to properly match each other. It is important that compression force must be applied such that rate of straining is constant. Yes, it is important because then otherwise if the straining keeps on changing, then the proper load will not be there and the proper contact between the two will also not be there. Most materials required to be tested in compression are viscoelastic in nature. Viscoelastic means that they had both properties, that is viscous also and elasticity also. Viscous meaning that they have a fluid type of property, they are slow in reaction, and elasticity means that whenever they are deformed then they come back to their original position. So viscoelastic materials. So these viscoelastic materials do not reach equilibrium readily. Like I told you, they are slow in responding, and so prescribed strain rates are therefore maintained. So now we will discuss about the universal testing machine. This is a very important machine which is used in the mechanical workshops, and it can do many types of activities. Like earlier we discussed the simple tension test machine. So this universal testing machine can do the simple tension test also as well as the compression test. So what it can do, now we discuss. It can perform tests like the tension, compression, bending, transverse shear and hardness. Whereas the any special machine, what it can do, it can perform only one special test like either the torsion or the compression test. So the types of this universal testing machine, what are the types? So there are 2 types. One is driven by the electric motor screw type, the other one is the hydraulic one. So the first one, electric motor type, it varies in size and capacity over wide range, ranging from few newtons to a few tons, whereas this one, the hydraulic type, it usually has high capacity. The second point is that in case of the electrically driven one, it has limited speeds of movement of crossheads so that the loads applied are within the definition of static. We have earlier discussed that it is a static tension test. So we have to look after this point, that everything should be as close as possible to static. In case of this hydraulic machine, same thing, limited speeds of movement of crossheads, so that loads applied are within the definition of static. Third point about these two machines, in case of the electric one, strain rates greater than 10 to the power minus 6 per second are usually not available. Similar is the case with the hydraulic machine also. But there are nowadays very sophisticated machines which are achieving strain rate up to the limit of say 10,000 or 100,000 per second. So now you can see the figure here also of the UTM machine, which is running with the help of the electric motor. So UTM also applies axial load. Like earlier I have demonstrated to you what was axial load. Whenever the load is acting along the axis of a specimen, it is axial load. So here you can see in the figure, this is the specimen and the load will be acting along its axis. Depending upon the positioning of the specimen, the load can act as tension, compression, shear or bending. So you can see, as I told, if this axial load is pulling it out, then it is tension. If it is pushing it towards the bottom, then it is compression, and if it is acting transversely, then it is shear. And if the load is acting transversely and it is fixed at one end, then bending can also occur. So these are the various kinds of loads that are acting on the specimen. Then the machine in general has two crossheads. I am showing you in the figure. This is the first crosshead, the top one, the bottom one is also there. So both of these are fixed crossheads. And there is a third crosshead which is positioned in between the two. You can see here this one. This is the third crosshead and this is movable. How it is movable? With the help of the screws. You can see these are the screws. When we change these positions, we can easily move this movable type of crosshead. So here, since it is named electric motor, you can see why we are saying like that it is electric motor driven UTM, because here you can see this electric motor is there. Then the gear and pinion are also there. These are moving the machine. So application of load is affected by the relative movement between the two crossheads. So you see here two crossheads, where accordingly the specimen will also move as they move up. Each machine has proper specimen holding and supporting devices to apply desired type of load upon the specimen. As discussed earlier, the load applied upon the specimen has to be balanced and measured, and as such each machine should have this device. So for this purpose, how we are arranging this load and how it is balanced, actually we discussed here. Fixed crossheads are supported over a compound lever system. So at the bottom you can see this is the compound lever system. On this the fixed crossheads are supported. And now you see at the end of this compound lever system, there is what? There is a balance weight, and it is operated with the help of lever. So you can see here this is the balance weight here, and this balance weight can be shifted to achieve balance of the lever. Suppose I am pulling it downward, then this will lift up, and accordingly here the movement will take place. So it is shifted to achieve balance of the lever and thus measure the applied force, and from this we can get the applied force, the force that is acting on the specimen. The balance weight is often replaced by a swinging pendulum also, whose rotation is transmitted to an indicator through gear train for direct indication of the load. So we can have this second mechanism also, and we can get the direct load also from it. So after discussing the electric motor type of UTM, universal testing machine, now we shall move to the other kind of UTM, that is the hydraulic UTM. So in a hydraulic universal testing machine, there is a slight difference as compared to the electric one. Here the rigid frame containing the upper and lower crosshead is attached to an accurately finished piston, which exactly matches with the hydraulic cylinder. So since the mechanism is changed a little bit, you can see here in the figure there is the hydraulic system. So a kind of cylinder, hydraulic cylinder is there, and in the cylinder the piston moves. So this piston is connected to the lower and the upper crossheads. The middle crosshead is the one which is adjustable, but it remains stationary when the load is applied upon the specimen. So here in this case, this middle one will not be moving as such. It will remain stable, but yes, we can adjust this position by the help of the screws which are given here. So what happens, suppose I am placing this specimen here in this portion, then suppose the piston goes up, so these two will also be going up, and this particular specimen will be pulled up, so the tension will be acting in this case. And if a specimen is at the bottom, then the compression will be acting. So an electric motor rotates a hydraulic pump that forces the oil into the cylinder, whereby the rigid assembly of lower and upper crosshead is lifted up. So here you see electric motor is again there, but it is not directly driving the your crossheads. It is, now what it is doing actually, it is just running a pump which is forcing the oil into the cylinder, and after this the crossheads will move with the help of this hydraulic force. The hydraulic pressure on the bottom of the hydraulic cylinder is transmitted to a hydraulic capsule which is connected to a Bourdon tube. So here this fluid is there, and this hydraulic pressure on the bottom of the cylinder will move the pointer on the Bourdon tube, so we can get how much force is acting with the help of this. And the middle crosshead can be moved up or down by separate positioning screws. It is just for the purpose of positioning, and it is not moving when the specimen is being tested. So here is the whole specimen given the figure, hydraulic ATM, which I showed you earlier also. So here is the upper crosshead, the lower crosshead, all the components of this machine are given here. This Bourdon gauge is there, you can identify and learn, and now the positioning, the piston is there, the cylinder, hydraulic cylinder is there. So you can just see the figure, and you can get what component is at which place and how it is working. Now we see that both types of machine, meaning the electrical gear driven machine and the other one which is hydraulically driven machine, both incorporate mechanical graphical devices to plot the load displacement curves. So this your stress strain curve can be got through these machines. Modern machines incorporate load cells for measuring the load and displacement gauges, whose electric signals, respectively proportional to load and displacement, can be plotted automatically on XY plotter when the test is proceeding. So this is a sophisticated kind of machine which are now being used in the current scenario. So these are sophisticated machines. So now we discuss what happens because of the strain rate. What will be the effect of the strain rate on the tensile properties of the material? So you can see from the figure also, static tensile tests are often performed at very low strain rate. It is about 0.001 per second, and variations permissible in conventional testing machines are generally so limited that they do not influence the static properties. This thing is very important actually, strain rate, because if the strain rate goes very high, then the type of load will change. It may change to impact load, like impact load is said to be above 10 per second. So it will be an impact load. Then what will be the benefit of this kind of load actually? It will not be useful, because we simple tension test or the compression test is a static type of test. So we try to keep the things static, and for that purpose what we do, we limit the strain rate. So it is given here, it is about 0.001 per second. So machines capable of varying strain rate by as much as 100,000 times have been developed. So this is also there, but for this tension test and compression test, we have to use machines which have very low strain rate. So tensile test in such machines have revealed, in the higher ones, it has revealed that tensile properties are quite susceptible to changes under increasing strain rates. So as soon as this strain rate is varied, so our tensile properties will get affected. So it's very important to keep the strain rate under certain limits. So what happens due to this actually if strain rate varies? You can see here in the curve that in general it is observed that yield strength and the ultimate tensile strength increase with increasing strain rates. So here in the curve you can also see, here you see that this strain is increasing very rapidly with respect to the stress. This is about 100 per second strain rate. and the lower ones you can see they are with lower strain rates. So these are the normal graphs where the strain and stress in the initial portion they are varying linearly. So that is the difference where it comes up when strain rate varies. Also, the percentage elongation seems to first increase with the strain rate but then decrease or remains constant. So in the second figure you can see here that the yield strength, it goes up very rapidly with increase in strain rate. Similarly, the ultimate tensile strength, it also goes up but not as rapid as the yield strength, and the elongation, it goes up but then it becomes constant after a certain time. So the load applied at a strain rate higher than 10 per second is classified as impact load, and under impact loads ductility of a material has tendency to reduce. So as soon as the load becomes impact type of load, meaning it is acting within seconds, high load acting within seconds, so it is impact load, and what will happen due to that? The ductility of the material will reduce. Like you can see here also, ductility is going down. Here in the top figure you see it is coming to the fracture point very quickly, so the ductility is reducing, the percentage elongation is reducing. So in this lecture we discussed about the ductile and the brittle materials compression test, and further we discussed about what is universal testing machine, both types of machine, hydraulic as well as electrically driven, and lastly we discussed about the effect of the strain rate on the tensile properties. Thank you very much.